Let's have a look at one more aspect of circular motion here now. Specifically, what I call vertical circular motion. Vertical circular motion is circular motion, object moving in a circle, but this time the circle is a vertical circle. We're not talking about a horizontal circle like going around a turn on a road, but we're talking about a vertical circle like, say, a roller coaster going upside down on a track. Now we can analyze the object going in vertical circular motion at an infinite number of places, but we're going to pick two places, the extremes. When we were analyzing horizontal circular motion, we usually only picked one because the motion of the object was the same no matter where you were. But when we're talking about vertical circular motion, because of the direction of forces, things vary depending upon where you are. But we'll look at the two extremes, the top and the bottom. Let's say for the top, we got a roller coaster cart upside down at the top of a vertical loop. Let's say for the bottom of the vertical loop, we've got, once again, a roller coaster car right side up at the bottom of the vertical loop. Now, what I want to do here is identify the forces that are acting on the roller coaster car in both places, at the top of the loop and the bottom of the loop. Tell me which force or forces act on the object at the top of the loop. Tell me one. Well, friction might act. We're going to ignore. We're going to ignore friction. We're going to pretend that none is there. But there would. The reality is there almost certainly would be friction there. Yep. Gravity. Which way does gravity act? Downwards. Good. So we're going to say Fg is a downward force. In fact, we're going to say that at the bottom as well. Force of gravity is downwards when you're at the top of the circle, and the force of gravity is downwards when you're at the bottom of the circle. It's always downwards, right? No matter what the orientation. Jack, what's another one? Okay, normal force. Which way does it act when you're at the top of the circle? Downwards, which is kind of weird, right? We've seen situations where the normal force doesn't cancel gravity, but we've never seen a situation where the normal force is in the same direction and helps gravity. This is one of those situations. The track pushes you down, gravity pulls you down. Now, we don't know which force is bigger. In fact, it depends upon how fast the object is moving. The faster you're moving, the bigger the normal force is going to be. There's a point, actually, if you're going slow enough, that the normal force is nearly zero. But as long as you're moving in that circle, then the normal force is going to be some. Okay? The centripetal force. We'll come back to that one in a bit. Okay? It's good. No, it's a good answer, but we're going to come back to that one in just a couple minutes. Okay? What other force do we have acting at the bottom of the circle? Yep. The normal force. Which way does the normal force act at the bottom? Upwards. And we know that the normal force, when we're at the bottom of the circle, is bigger than gravity. At the top, don't know. Depends on the situation. At the bottom, the normal force has to be bigger. Can anybody explain to me why the normal force has to be bigger when you're at the bottom? The net force must be toward the center of the circle. Otherwise, you don't go in a circle. So, if the net force must be toward the center, assuming we remain in the circle at the bottom, right? The net force must be toward the center. Then the upward force that acts toward the center must be bigger than the downward force that acts away from the center. Right? Now, just a couple minutes ago, Isaiah said there's another force, the centripetal force. The centripetal force definitely acts here. Definitely acts here. And we can't ignore the centripetal force like I said we were going to do for friction. But here's the thing. The centripetal force, we said yesterday and earlier today, is never a fundamental force. It's always caused by something else. Car going around a turn, it's caused by friction. The Earth going around the sun, it's caused by gravity. What's the centripetal force caused by here? Gravity and the normal force. In other words, the centripetal force isn't a third force, Isaiah. The centripetal force is gravity and the normal force. It's just another name for the combination of gravity and the normal force. What do you think the next step would be here? Calculate? No. I don't want to calculate the centripetal force yet. I will. I mean, that's right. I'm going to get to that. I don't want to do that yet. In order to solve for anything, we'd need the speed for sure. We need a lot more information than we have here. But what would generally be the next step in this general problem? Add the forces. F net is equal to the sum of the forces. That's what we do when we have a free body diagram. Now we're going to do that at the top and at the bottom, and for now it's going to look exactly the same. Now, Isaiah, I'm going to come back to you on this one because you know the answer to this. The net force will also be equal to what? We say that F net is equal to the sum of the forces, but F net is also equal to, usually we say MA, right? But MA in this case is M times V squared over R, or the centripetal force. So the net force is the centripetal force. Whether you're at the top or the bottom of the circle, the net force is the centripetal force. Now it comes down to plugging in numbers and solve, but you do have to pay attention to signs, what's positive, what's negative. So let's take a look at pos and negs, and then we'll solve a problem. You're at the top of the circle. Gravity, is it positive or negative? Why? Because it's downward, and it's always going to be downward, so it's always going to be negative. So let's write in that it's negative in both cases, at the top and the bottom of the circle. What about the normal force at the top of the circle? It's negative because it's downwards, which is kind of weird, right? Because usually, even if it's not positive, even if it's not upwards, it's acting kind of upwards. Here it's acting directly downward. We're going to make it negative. Normal force here is positive because it's acting upward toward the center of the circle. What about the centripetal force, which is not a separate force? It's the combination of those two forces. Okay, so which means if you're at the top of the circle, you said it's straight toward the middle. If you're at the top, where's the middle of the circle relative to you? Downwards. So we're going to make it a negative force. When you're at the bottom of the circle, which way is the middle of the circle relative to you? Above you. So it's going to be a positive value. Now, I told you we were going to analyze these two situations because they're the extremes. It is possible to analyze this situation. We're not going to do it, but I'm just going to show you one quick little thing to show you how it's possible, yet isn't necessary for us, okay? The values fall in between the top and the bottom, so we want our extremes here. How would we analyze this one? Well, we've got a force of gravity acting downwards, right? We have a normal force acting. So how would you deal with that? Well, you still have to add forces together, but you don't add them together. F net is equal to the sum of the forces. You add them together. Yeah. A squared plus B squared equals C squared, or X and Y components if you got a funny angle in there, right? Well, you could, but we won't. We won't. I mean, maybe if you take an engineering course at university or a physics course at university, you might see something like that, but not in Physics 20, we don't. Okay, these are what we're going to see in Physics 20, top and bottom, one-dimensional. Although, I mean, it really wouldn't be that big of a deal for us to see questions like I just showed you. We just won't see them, that's all. Okay, you got that? Plug in the numbers, solve. Let's do an example here. Page 264 says a bucket of water with a mass of 1.5 kilograms is spun in a vertical circle on a rope. The radius of the circle is 0.75 and the speed of the bucket is 3. What's the tension on the rope as shown in 5.31? Wait a second, we're swinging a bucket of water in a vertical circle upside down? Isn't the water going to go everywhere? Who says the water is going to spill out? Who says you can swing a bucket of water upside down and not spill the water? Oh, it depends on how fast. All right. Let's solve this problem here. I want to find the tension of the rope. Really, that's a normal force, right? I'm going to redraw this here. Normal force acting up, force of gravity acting down. We're solving for the normal force. You want to call it tension? Go ahead, call it tension, whatever. F net is equal to the sum of the forces, Fn plus Fg. We're going to say that F net is mv squared over r equals Fn plus Fg is m times g, right? Cancel out the masses. appears on both sides, but not in every term, so we can't cancel it out. M is 1.5, V is 3, R is 0.75. M is, what's M? 1.5. G is 9.81. We got to worry about signs here now. This one is positive because the center of the circle is upwards from you. This one is negative because gravity is always negative. Little shortcut here to do this in your head. 3 squared is 9. 1.5 divided by 0.75 is 2. So 2 times 9 is 18. 1.5 times 9.81 is 14.73, I believe. And it's subtracted because we added a negative value. Take that over to the other side. We get Fn is equal to 32.73 or 33 newtons. So the force of gravity or the weight was 15 newtons, 14.7 newtons. The normal force or the apparent weight is 33 newtons. You feel heavier when you're at the bottom of this loop than you do when you're just standing watching somebody in this loop. Did you feel that? When you guys were on the field trip 2 days ago, did you guys feel heavier when you were on the loop? Yeah. Yeah, and you kind of didn't know unless you're looking sideways. You kind of didn't know when you were right side up and upside down, right? It's weird. You're upside down and you have no perception of up and down at that point. All right. You have 2 questions to do here, page 264, 1 and 3. Take a stab at why I don't want you to do question number 2. We're looking for the tension, which is the normal force, that's fine, at position B. So that's this one, right? We just don't have to do it, so we're not going to. Questions 1 and 3, page 264 for homework for tomorrow.